discussed inferential statistics a little bit in this class, but today we're really going to dive into inferential statistics and why they're important. So first, let's review a little bit. What are inferential statistics and how do they differ from descriptive statistics? Well, descriptive statistics describe our sample, and inferential statistics allow us to generalize to the population based on our sample. So here's a basic recap of the definitions. Descriptive statistics are procedures for describing a sample, and inferential statistics are procedures for drawing conclusions about a population based on data collected from a sample. So when we obtain a statistically significant result, we are referring to the probability that the effect represents a genuine phenomenon in the population. Inferential statistics help us achieve a main goal. We want to generalize our effect beyond our sample to the population. Z-test. Z-tests are parametric inferential statistical tests of the null hypothesis for a single sample when the population variance is known. So here's that definition for you again. We're trying to test the null hypothesis for a single sample when our population variance is known. And we have two different types of z-test. First, we have a non-directional z-test, which is simply asking the question, does my sample mean differ significantly from the population? So for example, are IQ scores for students in 3010 different than the population? You can also have a directional z-test. Is my sample mean significantly greater or lesser than the population? So for example, are IQ scores of students in 3010 higher than the population? How are z-tests and z-scores different? Well, a z-score tells us about an individual in relationship to the sample, right? A z-test allows us to test our sample against the population. So let's look at these side by side. We computed z-scores comparing a single data point, one person's score, to its respective distribution of scores within that sample. Now we are computing a z-test, comparing a sample mean to a theoretical distribution of sample means called the sampling distribution. We're trying to determine, is our sample mean significantly different, significantly greater, or significantly lesser than the mean for the population? Now, one thing we've talked about several times is that we can't ever really determine specific things about our population, right? We can't ever really know a true and exact population mean because we can't sample the entire population. However, let's look at how we determine a population mean based on a distribution of sample means. So let's say that we want to take 10 samples from the population, 10 random samples for 10 different studies, right? Sample 1, sample 2, sample 3, sample 4, sample 5, sample 6, 7, 8, 9, and 10. So these are all 10 different combinations of samples that we took from the population. Do you see how they're starting to cluster together? Do you also see how they're starting to make a normal-ish type curve? Well, this is our sampling distribution. This is a theoretical representation of a plot of the means for all possible samples. If we took sample after sample, most would begin to cluster around the mean for a population. So for example, if we took sample after sample after sample of IQ scores, they would probably start to cluster around the mean of 100, which is the mean for the entire population on IQ scores. Now, knowing this, let's think about its relationship to probability. How likely is this to happen? For example, how probable is it that I got a sample IQ mean of 110 for our class? How likely is that to happen? So if we have a population mean of 100, and let's say this is our sample mean of 110, what we're trying to determine is how probable is this difference? How likely is this to happen? Well, we're going to have to do some math and compute some statistics to know for sure, but looking at this just visually, A sample mean of 110 seems pretty probable, right? It doesn't seem completely out of the ordinary or like this would just happen by chance. Now, all of this relates to the central limit theorem, and there's a really fancy definition that you'll get in just a second. But first, I just want you to imagine that you had to calculate those population means by hand. It would take forever, right? Well, that's where the central limit theorem comes in. Theoretically, the central limit theorem is what would happen if you selected every possible sample, derived every possible sample mean, and constructed the distribution of sample means, the DSM. Now, of course, this is never done in practice, but we make assumptions based on the population, about the population, based on the central limit theorem. Now, there are 3 assumptions of the central limit theorem, and don't let these trip you up. They're pretty simple. So for any population with a mean of mu and a standard deviation of omega, the DSM for sample size n will have, first, a mean of mu, second, a standard deviation of the standard error of the mean, which we'll go over on the next slide, and third, it will approach a normal distribution. So just refreshing our memory, in general, the standard deviation is how variable our data is around the mean. So what is the standard error of the mean? It's simply the standard deviation of our sampling distribution. So the standard error of the mean refers to the distribution of sample means around the population mean. How dispersed could you expect these population means to be based on chance alone? So let's look at this again. How likely is it that these means will vary just off of chance, right? That's what we're looking at. So this answers the question, what is the standard amount of difference between the sample mean and the population mean that is reasonable to expect by chance? And this is the formula we use to determine that, and it will always be provided for you when you have to use it. Okay, so we've gone over this a ton for a reason, but just one more time. Populations are almost always too large to actually obtain every possible random sample. We rely on mathematical assumptions about what our sampling distribution should look like instead. All statistics we use are based on the central limit theorem. So let's bring this back around to z-test and how we can determine if our sample is different from the population. Sometimes we ask questions that require us to find the probability of a mean. For example, what is the probability that 3010 students will have a sample mean of 110 or higher? If we know our population mean and the standard deviation, we can figure out how likely 3010 students are to have a sample mean of 110 or higher. So how do we use our sample information to calculate a z-test? A handy-dandy formula. Okay, so now we're going to work out a z-test. We have the same research question. What is the probability that 3010 students will have an IQ of 110 or higher? First, we set up our null hypothesis. The sample mean is not greater than the population mean. Then we set up our alternative hypothesis. The sample mean is greater than the population mean. And we use the SEM formula and the z-test formula to obtain this value. And basically what these are doing is subtracting the population mean from the sample mean and dividing that value by the SEM. So let's do that now. This is the type of information that you'll be provided with when you're asked to compute a z-score. So for this example, you have a sample mean of 110, you have a population mean of 100, a population standard deviation of 15, and an n, or sample size, of 30. Now first we're going to work the standard error of the mean. So we're going to take 15 and divide that by the square root of 30, which is 2.74. Then we're going to work out the z-test. We're going to take 110 and subtract 100 and divide that by our SEM, which is 2.74, which gives us the value of 3.65. So for this example, our z observed is 3.65. Now, how do we know if this is significantly higher than you could expect based on chance? Well, first, this z-observed value tells us how many standard deviation units is this sample mean away from the population mean. Using our knowledge of probability, we can know how likely or how probable we could get our observed z-value for the mean due to chance alone. And we do this by comparing our z-observed value with a critical z-value. We always set our alpha level or our p-value to 0.05 based on common null hypothesis testing practices in psychology. Now, since this is a directional hypothesis in the positive direction, we need to find the z-value that cuts off the top 5% of the distribution, which we'll call our z-critical value. So go to the back of your book, and in the left-hand column, I want you to find the value 1.64. If you follow that value over to the far right-hand column, you should see a probability value of p equals 0.5. So this is our z-critical value for this test. When we are testing a hypothesis, we call this area under the normal curve that falls beyond the critical cutoff point the region of rejection. Why? Well, if we want to know if our z-observed of 3.65 is greater than our z-critical of 1.64, we compare those values, and if it falls into that region of rejection, then we reject the null hypothesis. If that value falls into any part of the rest of the distribution, we fail to reject the null. Now, I prefer to look at this visually and demonstrate what it looks like because I think it's a little bit easier to understand, especially when you're first getting familiar with this information. So like we said, we had a z-critical value of 1.64, right? That means that everything to the right of that value is our region of rejection. Now for our example, we calculated a z-observed of 3.65. This value falls into our region of rejection. So in this case, we would reject our null hypothesis that the sample mean is not greater than the general population mean, and we would support our alternative hypothesis. Our sample mean is greater than the general population mean. Now, believe it or not, you just conducted the 4 steps of hypothesis testing for a z-test. You first constructed your null and alternative hypotheses. You then set up your decision rule by finding a z-critical value of 1.64. You collected data from a sample and calculated your test statistic and found your z-observed. Then you applied your decision rule, compared your obtained probability value of z-observed with the probability of 0.05, so your z-observed with your z-critical. Then you determine if you reject or fail to reject your null hypothesis. So let's practice a couple more of these. Dr. Livingstone says her students are brilliant, and she predicts her sample of 60 students' SAT scores with a mean of 540 would be significantly greater than that of the population, which has a mean of 500 and a standard deviation of 100. So first let's do our null and alternative hypotheses. Our null hypothesis, the sample mean is not significantly greater than the population mean. Your alternative hypothesis, the sample mean is significantly greater than the population mean. So now it's time to set up your decision rule. What z-critical value will you use? Well, first consider 2 things. You have a probability of 0.05, always, and whether or not the test is directional. Well, this is a directional test. She expects her students to do greater than the population, so it's in a positive direction. So we're going to use the critical value of 1.64. So now let's calculate our z-observed. For the standard error of the mean, we're going to take 100 and divide that by the square root of our n, 60, which is 100 divided by 7.75, which gives us a standard error of the mean of 12.9. For our z-test, we're going to take our population mean and subtract that from our sample mean, so 540 minus 500 divided by our standard error of the mean. This gives us 40 divided by 12.9, or a value of 3.1. So now it's time to apply our decision rule. Compare your z-observed value to your z-critical value. Do you reject or fail to reject the null hypothesis? In this situation, our z observed is 3.1, which is greater than a z critical of 1.64. So we reject our null hypothesis. Visually, we have a critical value of 1.64, meaning this is our region of rejection. Our z observed of 3.1 falls into that region of rejection, so we reject our null hypothesis and support our alternative hypothesis. The sample mean is significantly different from the population mean. Up to this point, we've only been conducting z-test on one-tailed test, right, with directional hypotheses. We suspected that our sample mean was greater than that of the population. So how would we go about testing a non-directional hypothesis? Which steps do you think are going to change in our 4 steps of null hypothesis testing? Take a look at an example of a two-tailed test. So you are the manager of a Kellogg cereal manufacturing plant. You want to know whether your sample mean will statistically differ from the mean specified by the company, which is 368 grams with a standard deviation of 15. You sample 25 random boxes and find a mean of 372.5. So let's identify our null and alternative hypotheses. Our null, the sample mean will not significantly differ from the population mean. Our alternative is the sample mean will significantly differ from the population mean. Now it's time to set up our decision rule. What z-critical value will we use? Now this is where things change when you're using a two-tailed test. We still have a probability value of 0.05, but it's non-directional. Because it's non-directional, instead of looking at one probability value that represents 0.05, we're going to be looking at using a probability of 0.025 on either end of the tail. Let's look at this in the book. I find that on page 210, figure 8.3 does a great job of demonstrating this. So when you have a single critical region of either negative or positive 1.64, you have one region of rejection. But when you have a two-tailed test, you have to have a region of rejection in either tail, meaning you divide the 0.5 by 2, and you have a 0.05 probability on either end of the tail. Now, if you go to your textbook and find the value 1.96, you'll see that it is associated with the value 0.025 on each tail. You use positive 1.96 and negative 1.96. So let's calculate our z observed. First, we're going to do our standard error of the mean, which is 15 divided by the square root of 25, which is 15 divided by 5, or 3. Now we'll do our z-test, which is 372.5 minus 368 divided by 3, or 4.5 divided by 3, which gives us 1.5. Now it's time to apply our decision rule. Compare the z observed to the z critical. Do you reject or fail to reject the null? In this case, our z observed is 1.5, which is less than the critical value we set of positive or negative 1.96. So in this instance, we failed to reject the null hypothesis. And let's look at this to see if it helps better make sense of it. So with the two-tailed test, we have two critical values, negative 1.96 and positive 1.96, meaning we have two regions of rejection. Now in this situation, our z observed, or the calculated z value that we got, is 1.5, and it does not fall into either region of rejection. It falls in the space between the region of rejections. If your z observed doesn't fall into either region of rejection, we fail to reject the null hypothesis and we support it. The sample mean is not significantly different from the population mean. So the sample of cereals that you took at the Kellogg's factory was not significantly different from that of the samples of the entire company. Now, the last thing that we're going to talk about today is statistical power. So statistical power is defined as the probability of correctly rejecting the null hypothesis. Now remember, we can incorrectly reject the null hypothesis and commit a type 1 error. Statistical power is a way to determine our probability of rejecting the null correctly. There are many things that can increase your statistical power. First, having a directional hypothesis increases your power to find significant results. So think about your critical values and your regions of rejection. For a one-tailed test, you have a single critical value and you have a single region of rejection that represents 0.05. For a two-tailed test, you have two critical values and two regions of rejection that signify 0.025 probability. A directional hypothesis increases our statistical power because it gives us more of a chance of falling into that region of rejection than a two-tailed test. Large sample sizes also increase our power. So let's think about the z-score formula or the z-test formula. It involves using the standard error of the mean. And when we calculate our standard error of the mean, we incorporate our sample size. And if you work through the math, you'll find that a larger sample size increases our statistical power. A z-test. To test the null hypothesis for a single sample when the population variance is known. So a z-test falls under the umbrella of inferential statistics. It allows us to test our sample against the general population and be able to generalize to that population. Okay, the 4 steps of hypothesis testing. First, we construct our null and our alternative hypotheses. Then we set up a decision rule. We find the z critical value associated with a p of 0.05. We then collect data from a sample and calculate the test statistic. So we conduct a z-test to get a z-observed value. Then we apply our decision rule. We compare obtained probability of z-observed, the result of our calculation, with the z for probability of 0.05, which is our z-observed versus our z-critical value. Now here's a visual demonstration of what that looks like if we have a z-critical of 1.64. This is our region of rejection, and anything that falls into that region of rejection allows us to reject our null hypothesis and support our alternative hypothesis. So we're going to do 5 or 6 practice problems with this today, and if you have any questions after today's lecture, be sure to reach out. So first, according to the U.S. Department of Education, full-time graduate students receive an average salary of $12,800 with a standard deviation of $1,800. The Dean of Graduate Studies at a large state university in Pennsylvania claims that his graduate students earn more than this. He surveys 46 randomly selected students and finds their average salary is $13,445. Is the dean's claim correct? Well, first, let's construct our hypotheses. Our null, the sample mean will not be significantly greater than the population mean. Our alternative, the sample mean will be significantly greater than the population mean. Now we need to determine our critical value. So this is a one-tailed test in the positive direction because this dean believes his students earn more than this, greater than the population. So we have a critical value of positive 1.64. Now let's calculate our z observed. We're first going to do our standard error of the mean, in which we take 1,800 and divide by the square root of 46, which is 1,800 divided by 6.78, and that gives us a value of 265.49 as our standard error of the mean. For our z-test, we're going to take our population mean and subtract that from our sample mean, so 13,445 minus 12,800, and then we'll divide that by our standard error of the mean. We get a value of 2.43. So now it's time to apply our decision rule. Compare the z observed to the z critical. Do you reject or fail to reject the null hypothesis? In this case, the z observed is 2.43, which is greater than our z critical of 1.64, so we reject the null hypothesis. Visually, here's our critical value, region of rejection, our z observed. It falls into our region of rejection, therefore we reject our null and support our alternative. So in this instance, the dean is correct. His graduate students do earn a significantly greater amount than the general population. Let's take a look at another. A health researcher read that a 200-pound male can burn an average of 524 calories per hour playing tennis, with a standard deviation of 45.9 calories. 37 males were randomly selected from a local tennis club, and the mean number of calories burned per hour playing tennis was 534.8. Do males at the local tennis club significantly differ from the general population? So first, our null hypothesis here is that the sample mean will not be significantly different from the population mean. Our alternative, the sample mean will be significantly different than the population mean. Now it's time to determine our critical values. Well, this is a non-directional test. We're simply trying to see if these tennis players are different than the population. So we have a negative 1.96 and positive 1.96 critical values. Now we calculate our z observed. So first we'll do the standard error of the mean. We'll divide 45.9 by the square root of 37, or 6.08, and that gives us a standard error of the mean of 7.55. Now for our z, we will subtract 524 from 534.8 and divide that by the standard error of the mean. This gives us a value of 1.43. So now it's time to apply our decision rule. Compare the z observed to the z critical. In this situation, the z observed of 1.43 is less than the z critical of positive or negative 1.96. So we failed to reject the null. Visually, we have our two regions of rejection. Our z observed does not fall into our regions of rejection. Therefore, we fail to reject our null hypothesis and support it. So in this case, the males at the tennis club did not significantly differ from the general population. A researcher wanted to study the effects of mentoring on intelligence scores. He wanted to know as a baseline what the average intelligence of his students were relative to the general population, as he feels they have above average intelligence. He used a standardized IQ test, which has a mean of 100 and a standard deviation of 16. The 50 students in his study scored an average of 102 on the IQ test. So first, let's set up our null hypothesis. The sample mean will not be significantly greater than the population mean. Our alternative hypothesis, the sample mean will be significantly greater than the population mean. And because we expect a positive direction in this test, we have a one-tailed test, and that gives us a critical value of positive 1.64. So let's calculate our z observed. The standard error of the mean, we're going to take 16 and divide that by the square root of 50, or 7.07, which gives us a standard error of the mean of 2.26. Our z, we're going to take 100 and subtract that from 102 and divide that by 2.26. This gives us a value of 0.88. And now it's time to apply our decision rule. Compare your z observed to your z critical. Here, the z observed is 0.88, which is less than our z critical of 1.64. So we fail to reject the null hypothesis. Visually, here's our critical value, our region of rejection, our observed score, which does not fall into our region of rejection. Therefore, we fail to reject our null hypothesis and we support it. So this means that the sample of students' IQ scores were not significantly greater than the general population. A rental car company claims the mean time to rent a car on their website is 60 seconds, with a standard deviation of 30 seconds. A random sample of 36 customers attempted to rent a car on the website. The mean time to rent was 75 seconds. Is the sample of 36 customers different than what the company average is for the general population? We have a null hypothesis that states the sample mean will not be significantly different than the population mean. We have an alternative hypothesis. The sample mean will be significantly different than the population mean. Here, because we don't have a direction in mind, we're simply trying to see if there is a difference between our sample and the population. We have a two-tailed test, which means we have two critical values, negative 1.96, and positive 1.96. Let's calculate our z observed. So for standard error of the mean, we take 30 and divide that by the square root of 36, which gives us 5. We then take 60 and subtract that from 75 and divide it by our standard error of the mean, which gives us 3. So now we apply our decision rule. Here, our z observed is 3, which is greater than our z critical value of positive or negative 1.96. So we reject the null hypothesis. Visually, we have our two regions of rejection, and our z observed falls into our region of rejection. Therefore, we reject our null and support our alternative hypothesis. You want to test primal screen therapy for effectiveness in decreasing symptoms of neuroticism. Neuroticism is normally distributed in the population with a mean of 35 and a standard deviation of 4. A sample of 22 neurotics is drawn for primal screen therapy. After therapy, symptom mean is 34. Our null hypothesis here is that our sample mean will not be significantly less than the population mean. So the idea here is that primal screen therapy will decrease symptoms of neuroticism. So you think your sample will be less than the population mean. Alternative hypothesis, the sample mean will be significantly less than the population mean. Now we need to determine our critical value. We have a one-tailed test, and we expect this to move in a negative direction. Therefore, we have a negative 1.64 critical value, right? So we're just looking on the negative end of the tail here, so we use the negative 1.64. Let's calculate our z observed. So we have a standard error of the mean. We take 4 and divide that by the square root of 34, which gives us a value of 0.69. Our z-test, we're going to subtract 35 from 34 and divide that by 0.69. That's going to be negative 1 divided by 0.69, and that gives us a negative 1.45. Apply your decision rule. Here, our z observed of negative 1.45 is less than our z critical, 1.64. So we failed to reject the null hypothesis. Visually, we have a z critical of negative 1.64. This is our region of rejection. Our observed is negative 1.45, so it gets very close to that region of rejection, but it does not quite fall into it. Therefore, we reject our null and we support it. A manager wanted to see if college students spend a different amount than the national average of $24.44 per shopping trip to a local mall with a standard deviation of $3.70. The manager surveyed 30 college students. She found that the average amount spent per trip was $53.37. So let's do our hypotheses. Our null hypothesis, the sample mean will not be significantly different than the population mean. Our alternative hypothesis, the sample mean will be significantly different than the population mean. Now here, our critical values will be negative 1.96 and positive 1.96 as we have a two-tailed test. We don't have a direction in mind. We simply think that the sample will be different from the population. Now we'll calculate our z observed. So for standard error of the mean, we have 3.70 divided by the square root of 30. So 3.0 divided by 5.48 gives us a standard error of the mean of 0.68. Our z, we will take 2444 and divide that from 5337 and then divide it by the standard error of the mean. And we get a value of 42.5. So now we apply our decision rule. Our z observed here, 42.5, is much greater than our z critical value of positive or negative 1.96, so we reject the null hypothesis. Visually, our z observed does fall into our region of rejection. Therefore, we reject our null and support our alternative hypothesis. College students do have different shopping habits than the general population.